Hello and welcome to part 2 of our little problem on candles. Sorry, the last part cut off. YouTube, time lengths. Previous two parts we wrote balanced equation for combustion of a certain form of paraffin, and we calculated how much energy would be evolved by burning 1 gram of that in a candle. Now in part 3, which is in my opinion considerably more involved than the previous two parts, we're going to talk about an additive to candle, or an additive to paraffin found in scented candles that you buy at the store. Problem part C says, scented candles have additional compounds mixed in with the wax that people can smell at very low concentrations. Linalool, a molecule with formula C10H18O, molecular mass 154.25 grams per mole, smells like lavender and can be detected whenever its concentration is greater than 0.8 parts per billion. If you're in a room with a volume of 2 times 10 to the 4th liters at a temperature of 25 degrees Celsius and a total pressure of 1 atmosphere, how many grams of linalool must be in the air for you to smell a lavender scent? Okay. I don't know if any of you have heard the term parts per billion before. They also use parts per million, parts per thousand. All that means is that, let's say, in parts per billion, for every billion atoms or molecules, a certain number of them are, for example, in this case, the linalool concentration, they say it's 0.8 parts per billion. That means for every billion molecules, there are 0.8 molecules of linalool. Now, think about that. That's a we're talking molecules here, not grams, not moles, just molecules. For every billion molecules, about 1 of them has to be linalool for you to smell it. Usually they use this in talking about, for example, purity of drinking water and things of that nature. I haven't seen it used in a gas problem like this, but why not? You could also consider that if you had more than that, or a considerably amount more than that, it could become, burning that candle could become toxic. But that's another problem entirely. Alright, let's begin with this problem. It's asking you how many grams it's saying you're in a room. That room has a volume of, I believe that's 20,000 liters. Correct me if I'm wrong. 2 times 10 to the 4th liters is the volume of the room, certain temperature, normal atmospheric pressure, normal room temperature, 25 degrees Celsius. This problem one thing I don't like about this problem is that it assumes that everything in the room is going to be a gas and air. I mean, it's a theoretical problem. It can't make sense. Because you have, usually in a room of a certain volume, you have other things occupying the volume. Furniture, people, etc. But we're going to just assume this room is a vacuum, there's nothing there, it's just a giant container with you inside of it, and your volume isn't accounted for. What happens there? There's nothing but air in that room. Air and linalool. Very small amount of linalool. Air is a gas. And there's one thing we know about gases. If we're given their volume and what temperature and pressure they're at, we can tell how many moles of gas there are. From that, we can tell how many molecules of gas there are, or parts. Parts, molecules, and atoms are all the same term. I'll just write that down for you. Parts equal molecules. They are the same thing. Alright. So now let's ask ourselves a question. How many molecules total are there if, assuming that whole volume of 2 times 10 to the 4th liters is all gas? How many molecules of gas are there? We don't know what they are, we just want to know how many molecules so we can tell how many molecules of linalool we need. We don't need to worry about what the composition of air is, if it's such and such a percentage of oxygen or whatever. We're not concerned with that. Just how many molecules of gas are there in that room? Well, we have the ideal gas law to tell that. PV equals nRT. Rearranged N equals PV over RT. Let's look back at our problem. What do we have? We have volume 10 to the 4th liters. We have temperature, 25 degrees Celsius, or usually you want to work with absolute temperature kelvins, 298 K. And we have pressure, 1 atmosphere, normal atmospheric pressure. Okay, so let's plug in that, what we got. Pressure, 1 atm. Volume, 2 times 10 to the 4th liters. R, don't forget to use the right R, because there are 3 or 4 of them depending on what units of pressure and volume you use. 0.0821 liter atmospheres per K mole. And the temperature, 298 kelvins. Now if you cancel off all of your units, liters, atmospheres cancel with this here, K cancels with that, you're left with moles, because that's in the bottom, so it's inverted, so your answer is going to be in moles, and you know you set your problem up correctly. We do the math on this, we get 8.18 times 10 to the 2 moles. That means that there are about 800 moles of gas present there. Don't know what kind of gas. We're hoping it's oxygen if we're going to be alive, but either way, that's how much gas is there. How many molecules of gas? Well, that's a simple step. We all should know by now how to convert from moles to molecules and back. So 0.18, I forgot the scientific notation there, times 10 to the 2nd moles. Put 1 mole on the bottom. 6.022 times 10 to the 23rd molecules on top. And that equals 4.92 times 10 to the 26 molecules. That's how many molecules are present there, gas. Now we want to find out how many molecules per billion need to be there. Well, we already know that for every billion molecules of gas there needs to be 0.8 parts or molecules of linalool. Alright, so let's find out how many units of billion molecules are there, because it's parts per billion. So we'll just divide the number of molecules we already have by 1 billion to find out how many units of 1 billion molecules there are. 4.92 times 10 to the 26. Billion is going to be 1, 1, 2, 3 zeros, 1, 2, 3, 1, 2, 3. Do that. Comes out to 4.92 again. Just change the scientific notation. Times 10 to the 17th billion molecules. Alright. So now we know that there are 4.92 times 10 to the 17th units of 1 billion molecules. Now I'm going to have to hurry up because time is running out on the YouTube time limit. Okay. So now all we need to do is multiply it by our parts per billion unit up here. 0.8 parts per billion. I'm going to write molecules per billion. And that comes out to be 3.94 times 10 to the 17th. I should have written Linalool here to signify exactly what I was talking about. But that comes out to that many molecules for that specific number of molecules of Linalool. Alright. Now all we need to do, the last step, is go from molecules to grams. And I'm going to leave you to do that and just tell you that after I did, I got 1.01 times 10 to the negative 4 grams of Linalool, or C10H18O. Good luck. Thanks for watching.